Okay, welcome back, everybody. So last week's topic was random variables and measurable functions, and the two terms are just the same thing, right? Random variables is the name that we use in the probabilistic context, but it is simply a measurability requirement on functions, okay? In other words, if the interesting events about the function that you define are interesting for your random experiment. That's the question that you ask to test measurability. And we found ways to check it in an easier manner by using the properties of sigma algebras and maybe some subcollections that generate them. If you look at the definition of measurability or being a random variable, it has nothing to do with probability measures or measures. So all you need in order to define a random variable or a measurable function is two measurable spaces. The setup of the random experiment and also the space for the values of the function. You don't need a measure. You don't need a probability measure in order to define a random variable, in order to talk about measurability. What we're going to do today and this week and also next week is the interaction between measures and measurable functions. So the first interaction that we're going to discuss is through integration. What is the integral of a function, measurable function, with respect to a measure, in particular a probability measure, which gives us the so-called expectations or Lebesgue integrals. Okay? And so that gives you a rough idea about an average value of a random variable if you're working in the context of probability spaces. And the next question will be, can we get some more information? Can we look at more interesting probabilities about a random variable? And that's going to be the distribution part, which we're going to discuss next week. So this week, we're going to discuss a simpler type of interaction between random variables and measures, and that's going to be integration or expectations. So that is our third section in the second chapter. Expectations and Lebesgue integrals. So if we have a measurable space, on one hand, we can have a measure on it, in particular, a probability measure. And on the other hand, we can have let's say a numerical measurable function. Since we're going to integrate them today, we need some values, numerical values, to be able to do integration. Therefore, this week, our attention will be focused on numerical measurable functions, okay? Random variable, let's say, okay? So what is the interaction between the two? So our aim today is to define a quantity x d mu, which will be called the Lebesgue integral of x. So this is the name of the mathematician who constructed those integrals, I think at the beginning of the 20th century. And that was, if I'm not wrong, that was even part of his PhD thesis. So that was an impressive work, which we still use today. Lebesgue integral of x with respect to mu. Okay? And in the probabilistic setting, so when mu is p, is a probability measure, we'll call it the expectation or expected value of x under p. And in this case, we're going to denote it by using this E letter. And if you'd like to make it clear that you're using P as your underlying probability measure, you put it like this, okay, sometimes with those square brackets. If the probability measure P is fixed in the setting and everybody knows what it is, you use this notation. But this is nothing but x dp, okay? That's the probabilistic way of writing the integral of x with respect to p, which is a probability measure, but also a measure. So therefore, we're going to construct integrals for a general measure space, okay? Prove properties about general Lebesgue integrals. And then, of course, they are also valid for expectations. And we're going to use them mostly in the setting of expectations. But sometimes we will need the full measure space structure. For instance, if you take an integral on R and you use the Lebesgue measure on the real line, so if your omega f is the real line with the Borel sigma algebra, in that case, if you use the Lebesgue measure, it's not a probability space anymore. So you sometimes need measure spaces that are not probability spaces. That's why we will construct the integral in the general way. Construction of integral. So the hope today is to define integral and make sure it satisfies nice properties. So there are one very nice property of expectations that probably all of you know from an undergraduate course. What is the nice property of expectations? Additivity. So if you look at expectation of x plus y, it is expectation x plus expectation y. And that is also a property for integrals, right? If you look back to calculus, you also have this kind of property. So we're going to call it linearity because you can also multiply random variables with constants. Okay, so that's going to be one nice property. And the other nice property is monotonicity. Okay, so if you have two functions, two random variables, one is always smaller than the other, then you would say that the expectation of that is also smaller than the expectation of the larger random variable, right? So at least we want those two properties. So we're going to do it step by step. Okay, let me first fix our measure space, omega f mu, okay? And x numerical function, let's say a measurable function. So that's an arbitrary measure space, and that's an arbitrary measurable function. So step one is if x is an indicator function or a Bernoulli random variable. For some, of course, we checked before that if this kind of a function is measurable, then this event here must be measurable and vice versa. Therefore, I require that A be in F, right? So then define the integral of x with respect to mu by mu of A. That's a very natural definition, right? If you look at the expected value of a Bernoulli random variable and use your undergraduate knowledge, what would that be? Well, it takes just two values, 1 and 0. So 1 times probability that it takes the value 1, which is this, plus 0 times the probability that it takes the value 0, which is just not there, right, because of the 0. So that's a very natural definition, and we know that this measure can take any value between 0 and plus infinity, including both values. So this definition gives you a positive value. And the easy extension of this is to simple functions, simple positive functions. So if x is a simple positive function, say x is of the form AI indicator capital AI, okay, where A1 to AM are positive reals, A1 to AM are measurable sets, and M is a finite number, right? Then define the integral of x with respect to mu by AI times mu of AI, which is also positive. So it's well defined. You never have infinity minus infinity since we're always looking at positive functions. So AI is positive, mu is positive, including plus infinity. Therefore, you get sum of positive numbers. So that's going to be between 0 and plus infinity. So it's well defined, and that is the expectation formula for maybe functions with only finitely many values, right? So AI is the value, and this is the probability that it takes that value, right? Of course, if it is the canonical representation. So there is one issue here. Let's call it a sanity check. You know, there was an issue about simple functions, right? What was the issue? Do you remember? Let's say I give you one way of writing x. Is there a unique way of writing it? We looked at an example, remember? A1 and A2 intersecting, right? And we defined a simple function which takes some value, A1, on the capital A1, and A2 on capital A2. So that was A1 indicator A1 plus A2 indicator A2. Do you remember this example? So in fact, when we say this function takes the value A1 on A1, this is not very correct because it takes the value A1 here, A2 here, but not here. It is the sum of the two values because of the intersection. And we even worked on this as an example, and there are many ways of writing this down, right? So if x has another representation, say x is equal to bj, indicator bj, now maybe not to m, but let's say to k, okay, then check as an annoying exercise that we get the same result. In other words, apply the formula, the definition, to this representation, and then to the other representation. The end results should match. Otherwise, you have problem with the definition. You have issues with the definition. It's a very annoying exercise, but it is valid, okay? Therefore, the definition in step 2 is free of the choice of the particular representation of X. In particular, you can even use the canonical representation, where you look at A1 on this set A1 minus A2. You look at A2 on the set A2 minus A1. You look at A1 plus A3 on the intersection, and you look at 0 as the value on the outside of A1 union A2. So that's the canonical representation. So let's look at an example. So as I just said, this is really like the undergraduate formula for expectations of discrete random variables. Let's say discrete random variables with only finitely many values. So let's say we are in the probabilistic setting, okay, omega fp. Okay, so X random variable taking distinct values x1, xm, and distinct values in this set, which is a subset of R plus. Okay. Then what the formula gives you, what the definition gives you, is the definition for expectation. Let me first write X. What is X? Well, X is a simple function taking the value xi on the set, on the event, x equals to xi. I to 1 to m, okay? So that's a simple positive function. So if we apply the definition, what we get is xi times the probability that x equals to xi. Undergraduate definition of expectation. Well, it is no longer just an undergraduate definition. It is also a definition when you have a discrete random variable with finitely many values. So it is just to give you the idea, that give you the feeling that we are doing the right stuff. Okay? We are doing the right thing. And since we are at it, I'd like to say sometimes we will just omit those parentheses and we'll just write this, the probability that x equals to xi. Sometimes we will omit those additional parentheses, which we usually use when talking about measures. That's just for brevity. So now let's check that this definition for simple functions, simple positive functions, this definition of integral satisfies monotonicity and linearity. Okay, let's check monotonicity and linearity. So, okay, basic properties. Okay. So let's write it as a proposition maybe. So let xy be simple positive. So here are some properties. First of all, the integral of 0 is 0, right? There is nothing to say about this. If you have a simple function which is always 0, so if it is 0 times indicator of something, you just get 0. So that there is nothing to check about it. Okay. Sometimes I'm going to call it nullity. Okay. So this 0 for null, and the integral of 0 is 0. Okay. Anyway, and the integral is always positive. Okay. So here is monotonicity. So x less than y implies expected value of x is less than, first of all, I should check linearity. So if you have AB, also positive reals, then the integral of ax plus by is a integral of x, b integral of y. Well, if a and b are just constants and x and y are simple positive functions, so note that ax plus by is also a simple positive function. Since all three integrals are defined as finite sums, and finite sums are linear, this property follows. You can write it down. You can take a representation for x, a representation for y, which is going to give you a representation for ax plus by, and then since each of those three integrals is defined through a finite sum, finite sums are linear, so you can just check it very easily. So I don't want to spend time on that. And finally, monotonicity. So if you have x less than y, this implies integral of x is less than integral of y. And here's why. Let's try to use linearity. Well, if you look at x and y, so this is also positive, right? So the gap between x and y is also positive, right? So in particular, you can write y as x plus y minus x. Now, this is positive, and since y is bigger than x, y minus x is positive. X is simple, y is simple, therefore y minus x is also simple. Because if simple means what? It just takes finitely many values. So if you look at the difference of two functions with finitely many values, the difference can also take only finitely many values. Therefore, they're all simple. So by linearity, we have integral of y is integral of x plus integral of y minus x. But integral of y minus x is positive, right? Because it is always positive, we know. Therefore, we can just bound it by x d mu. So y d mu is greater than x d mu. So far, things are not very difficult because we just look at random variables with only finitely many values, like binomial, Bernoulli, right? So the next step will be to extend it to arbitrary positive measurable functions or arbitrary positive random variables. And the idea behind this construction is an idea that we discussed last week. So do you remember how we approximate arbitrary positive measurable functions using simple functions? Do you remember this idea?
We use the sequence, and each time we get a finer partition of that simple function, so we just approach to that main function with simple functions.
Exactly, that's what we did. So what we did was to approximate, at the nth step, the values of the random variable between 0 and n, okay? And at step n plus 1, we approximated the values between 0 and n plus 1, and so on. And what we also do is to make the approximation between 0 and 1 finer and finer as we increase n. So that was a sequence of simple functions that are monotonically increasing with their limit equal to x, the original measurable function. So let me remind this to you. That's going to be the main part of the construction. So this is step 3. So let x just be positive. Recall, let's define, let's call it Zn, okay, which is Fn applied to x, where Fn was this. So you approximate your function by I minus 1 over 2 to n. If it is between I minus 1 over 2 to n to I over 2 to n, excluded, at x. So you do it up to n times 2 to n, which is going to end at the point n. So between n and plus infinity, you need to do something, and that's what you do because it is at least n, therefore you approximate it by n. At point x. And there should be an n here. So if x is between n and plus infinity, you approximate it by n. So the property was that, well, z1, z2, etc. are simple, and the limit is x. That's the reminder. Well, now here's the idea. If you have such a sequence, if you have such a standard way of approximating any positive measurable function using simple functions, and you have a way to integrate each of those simple functions by step 2, just look at the integrals of Zn's. Z1 less than Z2 less than Z3. Look at here, look at monotonicity. Z1 less than Z2 means what? Integral of Z1 is less than integral of Z2. Therefore, the integrals of Z1, Z2, Z3, etc. form an increasing sequence of positive numbers. And we also proved, maybe 2 weeks ago, that if whenever you have an increasing sequence, it always has a limit, but the limit could be plus infinity, it's fine. Therefore, that's the way we're going to define the integral of x. So by monotonicity of integral for simple functions, we have integral of z1 less than integral of z2, etc., and limit of integrals exist. Let's define this limit as the integral of x. And since it's the limit of positive numbers, it is also between 0 and plus infinity included. Okay.
For the integral?
It doesn't matter. It doesn't matter. And we're going to conclude it when we prove a convergence theorem. Okay? Indeed, yeah, you don't have to use this sequence of approximating functions, simple functions. You can do it in many other ways. In fact, what you can do as an alternative construction, what you can do is to look at all simple functions that are below x. So since they are simple functions and positive functions, their integrals are well defined by step 2. What you can do is to define the integral of x as the supremum of all such possible integrals of simple functions. And the two constructions give you the same value. We didn't follow this construction. And we're not going to prove they produce the same result. Okay? So there are alternative constructions. So one point here is that is step 3 compatible with step 2? In other words, let x be simple positive. We may define integral of x with respect to mu using both step 2 and step 3. Do they produce the same result? Now let's check it. Okay? So when we pass to the next step, it should always extend the previous step. For instance, compare step 1 with step 2. Clearly, every Bernoulli random variable is also a simple function, right? You just have m equals 1 and ai equals 1. And if you apply this definition to the Bernoulli, you will just get mu of a. So step 2 and step 1, they're compatible. Step 2 extends step 1. That's okay. But does step 3 extend step 2? Let's check it. Okay? So let's look at the canonical representation of x. Say x is a1 or x1 on this set and xm on this set. So we have some regions in omega where it takes distinct values, x1, x2, x3, x4. They partition omega, those events, x equals x1, x equals x2, etc. Step 2 definition gives x d mu is equal to xi mu of x equals xi. Just apply the definition, and we didn't check, but we said it is free of the choice of the representation, so we can use the canonical representation. That's what step 2 gives us. For step 3, let's look at fn applied to x, or this zn. Well, I can look at it in this set, or I can look at it in this set. Exactly one of those events is going to occur. We are either here, or here, or here, or here. So that's an omega-wise equation. That's for every omega, okay? Therefore, since it's an omega-wise equation, so for a fixed omega, here's what we can do. Use the fact that x is in fact equal to little x1 in this region. And use the fact that x is in fact equal to little xm in this equation. So I can write it as fn now applied to just this deterministic value, but I preserve my indicators, don't forget them. And fn applied to xm. Now, this is one representation of Zn. Zn is a simple function, and that's one representation of it. So step 2 gives Zn d mu is what? Fn at x1 times mu of x equals x1. Let me write it as a finite sum directly, okay? So just Fn x1, that's like A1, right? Times indicator, sorry, times the measure of this event. From I to M. And all we have to do is to let n go to infinity. Let n go to infinity to get the step 3 definition of integral of x. X d mu is the limit of zn's, integrals of zn's. And what is the limit of this finite sum as n tends to infinity? Well, that's a finite sum, therefore I can just write it inside the sum. Fn of xi mu of x equals xi, I from 1 to m. And now what is this? What is limit of Fn? Limit of Fn. What is limit of Fn? It's fx equals x, right? The limit of Fn's is the identity map. Those functions, they converge to just x as n tends to infinity. So this is just equal to xi, which produces the same formula. The two definitions of x d mu match. So no worries about compatibility of step 2 and step 3. Okay, so the natural next step will be to prove linearity and monotonicity for the extended definition. So we check linearity and monotonicity for integrals of simple functions. Now we have to check them for integrals of positive measurable functions. So we extended the definition, but we also need to extend the properties, nice properties. So let's start with monotonicity, okay? They're not going to be that trivial, therefore we're going to do them one by one. And so let's start with monotonicity this time. Monotonicity. So if 0, x, y are measurable, then the integral of x d mu is less than integral of y d mu. Same order. Okay, good. Here's the idea for the proof. The idea is that at least we have a starting point. What is the starting point? We have this property at least for simple functions. Okay? Therefore, the idea is always to reduce x down to its approximators, those approximators, prove the result for those approximators of x and y, and then let n go to infinity to get the same result, hopefully, for the original functions x and y. So this is indeed a kind of a lifestyle in probability theory and in those constructions. So whenever you need to prove a result about an arbitrary measurable function, an arbitrary random variable, there is a general recipe which works in some cases, in many cases. And the recipe is as follows. Okay, try to see if you can prove the result for an indicator function. Hopefully, it's a very simple proof, right? And then try to extend your proof for simple measurable functions, simple positive functions. and then take limits to prove the result for arbitrary measurable functions, arbitrary positive measurable functions. So that's the lifestyle. That's a standard recipe, okay? An approach that is followed, okay? And it is in the philosophy of the approximation of measurable functions. It is in the philosophy of the construction of integrals, step 1, step 2, step 3. And it is also in the ideas of the proofs that we do, okay? So let's apply this idea. Use the fact that we already have monotonicity for simple positive functions. So how are we going to do that? Of course, we have always our standard approximating sequences. So let Zn, now I'm going to put an x as a superscript, and Zn for y, Fn applied to y for each n. So the crucial point is that if x is always below y, and you're approximating both by the same type of functions, they're going to also preserve the order. So when you do their nth order approximations, when you do the nth order approximations of x and y, they're going to preserve the order. The nth order approximation of x will be less than the nth order approximation for y. So that's an observation. X is less than y if and only if indeed Znx is less than Zny for all n. Because you're not approximating them using different functions. You're approximating them in the same way. Namely, by just plugging in the values of x and y into these functions. And these functions are increasing functions. So if you plug in x, the realization of x and the realization of y, so the Fn at the realization of y will produce a larger value because it's a step function that is increasing like this. X, Fn, x. And at some point it stops, right? At n, it stops. So it's a function like this. Therefore, if you look at the realization of x of omega and y of omega, so that's going to produce a larger value. And it is if and only if, because if you have this for all n, just let n go to infinity, you will get the limit of these is equal to x, the limit of these is equal to y. So we have the integral of x is less than the integral of, the integral of Znx is less than the integral of Zny for all n. And let n go to infinity, we get what? So the limits of those give you the integral of x less than integral of y. Okay. So then next, let's try linearity, okay? So you have xy positive measurable and ab, then integral of ax plus by is equal to a times integral of x, b times integral of y. Now, I gave you a recipe, so let's attempt using it again, okay? So, we have if you use the same notation as before, so if you look at integral of not ax plus by, but A times the approximator of x at step n plus the B times the approximator of y at step n. This gives you A times znx d mu plus B zny d mu by linearity in step 2. So let n go to infinity. We have limit of znx d mu equals integral of x d mu. Limit of zny d mu is equal to integral of y d mu. But limit of a znx b zny plus d mu, we don't know if this is equal to the integral of ax plus y, because we don't have in general that this is the approximator of ax plus by. So this approximation business, it preserves monotonicity, but it is not a linear thing. Just to give you an idea, let's take a equals 1, b equals 1. So let's try to approximate x plus y, okay? Let's apply fn to x plus y. What's happening there? The regions for x and y, they overlap. X takes some value on a region, y has another value on the same region, and you add them. So how are you going to approximate x plus y using the approximations of x and y if they have values on common regions? Okay? So in general, we don't have this. We don't have in general that we have this not equality. We don't have the equality. Okay. So let's give a break, and we're going to find a way to fix this proof.